Now we're moving to more properties of a normal distribution, okay? And then once we cover those, we're ready to do certain calculations about normal distribution, answering questions in real life, okay? So first of all, there's the 68, 95, and 99.7 rule, okay? You probably have heard about this before, but what we're showing over here is a graph, okay, of any normal distribution, okay? A particular one, I guess I would say, with mean, mu, and then sigma, but it's any, because you can put any mu and sigma out there, okay? So mu is the variance, sigma is the mu is the mean, and sigma is the standard deviation. So what this rule is telling us is that if a random variable x has a normal distribution, then about 68% of the probability gonna fall into within one standard deviation of the mean. Okay, when we say within one standard deviation, we're talking about mu minus sigma to mu plus sigma. Okay, so this is in this shaded, like the lightest in the middle is the 68%. Okay, and then about 95% probability of x falls within two standard deviation. Okay, so it's mu minus 2 sigma to mu plus 2 sigma, and that's 95%. And lastly, mu minus 3 sigma to mu plus 3 sigma is going to be 99.7%. Okay, so what this is telling us, and lastly, the probability of x falls 4 or 5 or more standard deviations away is very low, because you can see that like within 3 is already 99.7%. So whatever remains, like all of those ones, okay, the probability only add up to 0.3%, and that's what we mean by it's going to be very low when you're looking at that probability. Okay, so this is true for any normal distribution with mean mu and variance sigma square. Okay, and what this is saying is that, well, we first of all know that its center has center and mu, right, based on what we know about the PDF of a normal anyway. But then the normal distribution is specific or very special in a way that it has this certain probability associated with how likely a random variable, if it follows a normal, how far away, right, it is gonna be from the mean. Okay, so 68% of the time, right, you're gonna be within one standard deviation, 95% within 2, and then 99.7 within 3. Okay, so that's true for any normal, and that is only true for normal. Okay, and we'll see how we can apply this rule in practice. All right, lastly, we do use notation, list phi. Okay, so small phi, okay, of x. Okay, it's the PDF of a normal, okay, and then this capital phi, okay, with x, okay, it's the CDF. Okay, so remember we used fx and fx before, right? That's very generic for any continuous random variable, or even, yeah, continuous random variable like the PDF and then the CDF, right? And then remember we used px and fx. That was when we were using for the discrete. Okay, but now we have specific notations for for the normal, just because it's so widely used. Okay, so we use small phi x to denote the PDF, and then capital phi x to denote the CDF. Okay, all right. So then lastly, in order to do any kind of probability calculations for a normal random variable, we usually bring it back in terms of z. Okay, so z, if you remember, okay, is doing random variable minus its mean divided by sigma. Okay, so this process is called like standardization. Okay, so for example, like if you have a bunch of x's, right, like x values, okay, and they can be all kind of ranges, right? But if I subtract the mean from each observation, okay, and then divide it by the standard deviation, we are standardizing it. So this is gonna be like what we're doing over here, right? Like x follows a normal with mu and sigma squared. And then once we do the standardization, it's gonna go back to the standard normal distribution, so we can work with all the probabilities calculation with mean 0 and standard deviation 1. Okay, so for any random variable, normal random variable with mean mu and sigma square variance, you can always do this standardization. Okay, so when that happens, okay, so the probability, okay, if I want to compute, right, the probability of my random variable, a normal random variable with mean mu and variance sigma square, falls into the range of A and B, right? That's the probability calculation. Okay, I can always bring it back, so you can see, to the standard normal. Okay, so as we know, z is x minus mu, right, divided by sigma. Okay, so well, by this, the inequality holds when I do a minus mu divided by sigma, and then b minus mu divided by sigma. So okay, so all of this is good. And once we do this, okay, you will see that because this PDF and CDF are for the standard normal distribution. Okay, so we're able to directly do that. So remember, when I'm trying, whenever we're trying to get the probability of a random variable falls into 2 points, okay, 2 endpoints, it's equivalent of getting the CDF at the larger point, right, minus the CDF at the lower point. Okay, and then that completes the steps. Okay, so just so you know, the reason why we're doing this is because later you're going to see, and you probably have known about this, there is a standard normal probability table that you can consult. Okay, so that's always about the standard normal distribution. Okay, so for example, like soon you will see that, well, if I want to know, like say, if I have a particular value here that I want to know, like say, let's just say 1.5. Okay, if I want to know phi 1.5, okay, what that means is that I want to know the CDF, right, evaluate at 1.5 for a standard normal distribution. Okay, and when that happens, you can consult a table, and the table going to tell you like what is the CDF value is. Okay, so that's why we bring it back in terms of Z, the standard normal, just because, well, whatever normal that you start with mean, mu, and variance standard deviation, you can always bring it back to the standard normal, and then we only need one table to consult. Okay, so that table is only for the standard normal table, and it's actually at the bottom of the Moodle page as well, called standard normal table. And then we're going to see an example now how to utilize that. Okay. Alrighty. Okay. So the example is this. Okay. At Heinz Ketchup Factory, the amounts which go into bottles of ketchup are supposed to be normally distributed with mean 36 ounce and standard deviation 0.11 ounce. Okay. And this is a normal. So we know that mu is 36 and standard deviation is 0.11. So sigma is 0.11. Okay, so sigma square, you have to square that. All right. So once every 30 minutes, a bottle is selected from the production line and its contents are noted precisely. Okay. If the amount of ketchup in the bottle is below 35.5, 35.8 ounce or above 36.2 ounce, then the bottle will fail the quality control inspection. What is the probability that the amount of ketchup in a randomly selected bottle is less than 35.8 ounce? Okay. All right. So we know, okay, if I use X represent the amount of ketchup in a bottle, right? We know that it follows the normal distribution with mean 36. Okay. And standard deviation is 0.11. So square of that is the variance. Okay. And I will also show you, and let me actually just directly bring that figure so it's easy to read over here. Okay, it's always very useful, I would say, in this kind of normal probability calculation to sketch a graph to see what exactly you're computing for. Okay, so we know that it's about a shaped symmetric distribution, right, for a normal. So we know that the mean is 36, so center at 36. Okay. And then we know the standard deviation. So standard deviation, you can just write it out over there instead of drawing it. It will be hard. But for us, it's important to look at what exactly we're doing here. It's asking what is the probability that the amount of ketchup in a randomly selected bottle is less than 35.8 ounce. Okay. So this line, let's just say 35.8. Okay. And we do a shaded area of the probability that we're trying to compute. Okay, so this is what I mean by it's very important to, I think, and useful to do a sketch so you know what exactly you're computing. Okay, all right, so keep this in mind. Okay, so now let's do what exactly we're going to do for the calculation. And just don't forget, if we come back to the previous slide of how to do probability calculation, remember we always bring it back to the standard normal, so then we can consult what I mean, a standard normal table, which I'm going to show you in a second as well. Okay, so to bring it to the standard normal scale, okay, so what we do, right, is we use Z equals to X minus mu divided by sigma. So X, right, that line, whatever that we're trying to compute below that point is 35.8, mean is 36, okay, standard deviation is 0.11, okay, so you compute what we call like a Z-score is negative 1.82, okay, so like we showed before, the probability of X is smaller than X, will be equivalent to the probability of Z, right, smaller than X minus mu divided by sigma. Okay, once we do the standardization. Okay, so this is equivalent to this. Okay, so that's why we're able to replace the probability of X smaller than 35.8 with the probability of Z is smaller than 1.82. Okay, so this number, how do we come up with that? This is what I mean by a normal table. Okay, so if you consult the table that I posted on Moodle, it's much more detailed. Okay, like it has two sides. Okay, one side is about Z is positive, the other side is about Z is negative. We're consulting the Z on the negative side because our calculate Z is negative 1.82. Okay, so what you do is so the first decimal point, okay, after the first decimal point, you should look at the column. So this particular column over here, so for us is negative 1.8. So we concentrate, okay, on this row. Okay, so okay, and then each column, as you can see over here, is telling you the second decimal point. Okay, so we focus on the second one or the third one over here because it starts from 0.00. So this particular value, okay, is is the PDF, the CDF, sorry, for this one negative 1.82. Okay, and for us, okay, if we come back to the plot one more time, okay, and the CDF, like I told you on the table, is showing you the CDF up to that point. And is exactly right this area that we're doing. So like this is the, like if I look at this plot, this is like in order to compute the probability, right, for the shaded area, it is the CDF of this normal distribution, right, evaluated at 35.8. Okay, so that's why whatever we're reading directly from the plot, from the table, will be exactly what we gonna do. Okay, so this probability 0.0344 is what we are getting from the table. Okay, just so you know, sometimes when you're doing, so not this example, but then when you're doing like a sketch, you realize, oh, I need to find this part. Okay, I want to know, like say this area. Okay, so when that happens, well, you know that the CDF for this point, once you do the standardization, gives you everything. Let me use a different color. Gives you everything up to this point, right? So if you want to know about this point, okay, what you need to do is that you need to do 1 minus whatever the value, the CDF value that you have computed for, I don't know, this value. Let's just say it's A. Okay, so that's why it is very important and useful to sketch out exactly what part of the area you're actually evaluating the probability for, because one way or another, you will sometimes, like say, if you do this particular example, is directly the value from the table. But then if you're doing something like this, you will need to do some more calculation about it.